Good morning, all the participants. Good morning, Puneet sir. Puneet sir, good morning.
Sorry, I was on. Yeah, good morning.
Yeah, sir, till now 57 participants joined, so we should wait
So,
for
so we wait
another. Yeah,
5 more minutes. Okay.
sure. Okay. Yeah. Thank you, sir.
All right.
So can we start, sir? Puneet, sir, can we start?
I was on mute again, so I will start now.
Yeah, sir, I have already given you the privilege to share the screen, so you can
Alright.
just check. Yeah.
Okay, just give me a second. Okay. Yeah. So we can start now, and what we'll do is just a minute. Um, give me a second. Yeah. So if my screen is visible, I've created another download, which you people need to download for all the further exercises. So this is beta 9, and it also has an ARM binary. So you need to download both. All right.
Okay, sir.
So need to download both. And once you download, these are the instructions to install Embedded UVM. Kindly download the binaries and untar the same using the following commands. So you need to untar the main release, as well as you need to untar the um, ARM specific release, which will create binaries that can be run on the basically the kit. Okay, so which can be run along with the FPGA map design. All right. So give me a second. What I'll do is I'll run my VNC so that I can follow the steps with you people. Okay. So okay. So I have my VNC running, and I can open the VNC here now. Okay, still not there. I need to check what happened. Give me a sec. Seems there is some issue with the server. Let's locate, let's say what the issue is. So I have my server named Swasti, and it's not visible on the, so it's visible only with IPv6 address. It doesn't have a IPv4 address, which is required for VNC. So I'll reboot my server and then hopefully we'll get it. This will take about 2 minutes. So we need to wait. Okay, meanwhile, you people can start the download. So Swasti doesn't have IPv4 address for some reason. I don't know. It happens once a while, but it has happened today. So I can SSH to Swasti, but I can't access VNC from there because VNC address that I have to provide is IPv4 based. So we need to wait for a couple of minutes. Okay, meanwhile, you can start downloading the stuff, the binaries from from the server. As I told you, basically you need to go to the download area, and from within the download area you will see a beta 9 release. We need both the files. So there is a release for there is an update on the main binary, so that I fixed some errors, as well as I have provided a binary which runs on ARM uh, processor, and therefore it can run on the kit, on Cyclone 5 kit. Okay, and we need to, after downloading, we need to untar the files, and then we need to do some basic setup which will solve some issues which you people were getting earlier. So there is an extra step over here. We need to run setup. Okay, so let me see if I'm able to access my server now. Okay. I need to try opening it again. Okay, now it is opening. My password, and here we are. All right. So now uh, I need to go to applications, and there I need to open the terminal. So I can get somewhere system extern. Okay. And since it's too small, so I ran xrdb, sorry, xrdb, so that's of resources extern, and I close this terminal and open again. All right. So this is my terminal. So I'll repeat the steps that you need to do for downloading. You can either use a browser for downloading, or if you're on Linux, which probably you are, because these binaries are for Linux. So you need to, so I'll remove most of the stuff from here so that I can have a clean directory. So remove minus -r star. So now I have a clean directory, and then I need to run wget http, let me bring it to the top, and then download dot uvm.io slash euvm 1.0 beta 9 and .r.xz. So it has started downloading, and it will take about 20 more seconds. So it's downloading quickly. And then once this download is complete, we need to download the ARM binaries as well. The ARM binaries have a suffix ARM Linux GNU EABIHF. Okay, so that suffix we have to provide. All right, so ARM Linux GNU EABIHF. So we need to give ARM Linux GNU EABIHF. Okay, so this download also started. It will take about 10 seconds. All right. So once both the downloads are complete, what we need to do is we need to untar this. So I'll untar. So this is the main release getting untarred. So in case you are just going to run it your on your Linux box, which is Intel machine, basically x86 64-bit processor, then you don't need the ARM binaries, then you need only this much. But since we'll be using the ARM binaries today, so we need to untar the other one as well. So I untar the other one as well. So it will again take about 5 seconds. Okay. So now we got a release here. And if we go inside this, we'll see in addition to lib, there's a lib arm linux gnu e abi hf. So this folder also got created. Okay, now you need to run a script after downloading. So you need to run util/setup. Okay, it will take a couple of seconds and then it will give you a message asking you to set this path, asking you to add this line in your .bashrc. So you can do that, or if you are running it only for this session, then you can just copy paste it and you're all set. So now if you say type LDC2, it should give you where it is coming from. All right. Now having done that, I'll take you to the workshop exercises that will be doing today. So the first exercises, we are going to run AVMM SHA3. And in AVMM SHA3, I have a test bench. And in the test bench, I have the normal stuff. And I have made some modification to the test bench. But that's most of it. And then I need to go to dot/sim directory. And there I'll say make clean, and so that I just have a make file, and these two files also I need to remove and then start. Okay, I have a make file now. Okay, so now I can make my test bench again. Okay, so this time I have also provided a setup so that the linking issues that you were getting earlier. So unless you are using some very old operating system, those issues shouldn't come. I haven't taken care of CentOS 7 version though. So if you have CentOS 8 or any recent Ubuntu version like Ubuntu 16, Ubuntu 17, Ubuntu 8, 16, 18 or 20. So any release that got, any Ubuntu release that got released in last 4 years, you should be fine. So as usual, for me, it created a VPI file and I'm able to run my simulation now. Okay. So now we are going to make some changes here. Okay, so it's taking a bit because it has 100 sequences to go. And when I say make -n run, then you will see I have given verbosity as none in the make file. I modified it. So let me put it to medium so that we can see the sequences running. Okay, so this is what we were doing earlier as well. So the same thing. Now I'll be checking in this stuff uh, into GitHub so that you people can repeat these steps. But for now, I'm doing just that much as I was doing earlier. So if I say make -n run, then it gives me the command, and now I'm going to make some changes here. So I'll keep this to none. I'll keep verbosity to none, and then I'm going to add a flag, and that will say plus UVM set type override equal to AVMN SHA3 dot SHA3 sequence item, comma, and I need to then override it. So I have created sequences which are like remainder 0, for example. And now let's see what happens. So now you will be seeing a message from UVM. Basically, I'm printing that message. I'll show the changes why this message is getting printed. So the factory configuration is getting printed. And in the factory configuration, it is saying that for this type out here, it has been overridden by another type. All right. So let's see. Now I'll enable my messages, and as I do that, I'll also key the output into a log file, and let me name the log file by the name of the sequence that I'm running. Log. There's some problem. I haven't given T over here. That's why I don't think got confused. Okay, so the log is getting dumped on the terminal, as well as it is going into the log file by way of the T command that I gave. Okay, so we'll be able to open the log. But before that, let's run it again, and this time without the override. So now, because it's the original sequence, so I run it with sequence item. I basically store the log into a different file. Okay, and then I'll also run it with another sequence, that is the empty sequence, and this time I'll yet have another log file. This will be quick because all the packets that are coming in, they are all empty. Okay, and finally there is another one which is um, remainder 1, and there also remainder 1. Okay, so all these 4 sequences we have run, and each test case is running 100 sequences or sequence instances for each of the test case. And now let's look at the log files and see how that. Okay, so we have the 4 log files. So there is remainder 1, remainder 0. So let's compare the original one with remainder 0 first. So see, in the beginning, you get a message which is saying applying override from the command line. And since we had given a command line override, and then in the since we are also dumping information on the factory, so there's the information on overrides which is coming extra because the other one doesn't have the lower one doesn't have an override, only the upper one has an override. Okay, so then since we use the factory, some more classes got registered with the factory. This is slightly different from how it happens in system Verilog, because of some technical intricacies. So in system Verilog, all the classes that you are using, they automatically get registered with the factory. And in embedded UVM, only the ones you are trying to use actually used by way of factory overrides, etc. Or even the random test is coming by way of factory. So wherever you are trying to use the factory, only those classes get registered. The other ones don't get registered. So registration of classes in the factory in embedded UVM is lazy. It happens slightly delayed depending on the need. Okay, and then you will see at most of the places you will see the pattern is different. Okay, so here, for example, you will see rate is 72 and the size is 216, which is exactly 3 times 72 because we are running um, remainder 0 as a sequence. And here the rate is not even specified because I'm using the base sequence item class, and that doesn't have rate specified. And you will see the phrase length is arbitrarily sized. It doesn't have, for example, here it's odd number of bytes. So this is the base class and this is the derived class. And we are able to run both of them using factory overrides. So let's now get into the code and see how the factory overrides are working. Okay, before that, I just wanted to show you the empty brackets, the empty phrases. So all the packets, all the SHA3 sequences that are coming here have phrase length of 0 because that's the constraint we gave in the. So you have phrase length 0 everywhere. All right. Okay. So now let's go into the place and go into the code and look at the source of the test bench. So you see, I have the default sequence item, and in the default sequence item, you have already seen it. And then in remainder 0, I'm putting a constraint which says the phrase length has to be an exact multiple of rate. And rate is defined as 200 minus 2 into outsize divided by 8 because outsize is in terms of bits. It's not bytes. Okay. And then I have another one, remainder 1, where I want to put it in such a way that the phrase length, when we divide it by rate, then we still have rate minus 1 over here. So that means it's the last frame will be almost full, only 1 byte will remain. So we wanted to cover that special case where the two delimiters 80 and 06 they get overlapped. Okay, and I also have an empty one where I put an extra constraint, and that extra constraint is that the phrase length is going to be 0. It's going to be 0 all the time. All right. So now with having overridden, in a way, not overridden, having extended the item class, okay, I'm able to choose any one of these extended classes. And day before yesterday, we had done the same lab, but in such a way that we were actually forcing this sequence instead of the normal sequence. So we had to create new test cases. So this is a test case, random test parameterized, and since it's a parameterized test case, so it has to be extended to create a normal test case. So we had to do all this stuff. So just for making sure that I'm taking remainder 0 um, as the test case. Okay, as a sequence in the test case, I had to create a new test case, and the same thing I'm doing now by by way of you know instead of uh, creating a new test case, I basically override the sequence. Okay, now so hopefully it's all clear, and basically it works that way, that factory whenever I'm requesting, so you will see it here. So whenever I'm creating, so this one is, this one is the SHA3 sequence. Yeah, I'm interested in this. So basically, when I'm creating, so this create will be of the type, because the sequence has this as a sequence item. So when I create this sequence item, and this sequence item uh, will be created by way of the factory, because I'm not using new here. So let's do an experiment. Okay, I'll do it later after I can complete this explanation. So because I'm using create over here, and create invokes the factory for creation of this component or this sequence item. So the factory is overridden now. And since the factory is overridden, the actual sequence which gets created is of the type of the extended sequence, of the derived sequence, wherein I put extra constraints, and those extra constraints also have um, constraints for uh, on the length of the phrase, so that we can cover those corner cases. Okay, so now instead of this, if I just go ahead and I just say, so request is my type, and I say new. Okay, so this is, I'm not invoking the factory now. I'm just using the constructor directly. And when I do that, and then I compile the test case, because we made a change, so we need to recompile. Okay, now when I compile the test bench, and when I run it again, and this time again, I'll run it with one of the factory overrides. So this is with remainder 1 as factory override. So let's make it remainder 0 factory override, for example, and just so that, because earlier we saw the remainder 0 log file. So I'm going to overwrite that log file, and now it's remainder 0. Okay, so I'm running it again, but this time I'm not invoking the factory. All right, but since I haven't invoked the factory, so you will see in the log file, though there is a factory override, but the test pattern wouldn't change. The stimulus will not have the new constraint. So now, okay, I need to show this and compare it against the original one. So, you see, here you have an override. So that override information is there because um, we actually from the command line said that we want to override, but then if you see the stimulus, it's exactly same, only the IDs of the objects, they have changed, and they changed because during the factory override, some new, the override process is implemented in such a way that some new objects get created. Okay, now if you go till the end, the stimulus is exactly same. There is no change in the stimulus. Only the object IDs are different, which doesn't have any significance or any uh, implication to the stimulus which gets generated. All right. So therefore, what I want to point out is when you are using overrides, if you want to use overrides, then you should invoke you should generate the particular request using factory. So here now you are using factory. When you say request.typeid.create in system Verilog, it will be request colon colon type ID colon colon create. But here it is request.typeid.create, and then you are invoking the factory uh, for creating a sequence item or a sequence, basically an object of either of type sequence or sequence item, but then this gets created using factory. And then you have the flexibility of overriding the, the type in factory and creating, actually creating, whenever you are creating using factory, the override information will be used, and an object of the derived type will be created instead of the original type. Okay, and thereby we are able to create the different scenarios or cover the corner cases. All right, now we move on to how to run the same test case on the kit. Okay, so we'll go step by step. Okay, so first of all, I have already created a I've already created a test bench for DE10 for the kit. Now we need to see how it is different from the test bench that we are using. So now let's first forget about the thing that we are going to use it on the kit. So it's going to be ARM architecture. That's the compilation part. But we are right now we are focused on what would be the changes in the test case. Those are required to make it run on the kit, because we are not interfacing with Verilog now. We are actually going to run it on the kit. Now, one thing, so this is what I'll be doing today. I'll be compiling this test case. I'll be running it on the kit, and when I do that, um, I'll also be putting a design on the kit. So I'll go through that process of how to compile the design. Though we already did it in yesterday with Ritesh, or basically I think it was before yesterday. On the second day itself we did it. Did a similar exercise, but yesterday also we did some design compilation, but that was for GHRD, for the Golden Hardware Design, hardware reference design. Today it's going to be our own module, that's the SHA3. So we'll basically follow the same steps, but then we will be doing it for a different design. And then once we create the bit file, we'll see what changes need to be made in the operating system to make that peripheral, which will be sitting now. It's not really a peripheral because it doesn't talk to the outside world. So it's an FPGA accelerator. So it will sit now on the FPGA. It will get mapped to the FPGA. But since it's a new hardware device for the whole system, we need to basically change the operating system, and there's something called device tree. We will be modifying the device tree to make this design accessible to us. Then we will test whether the design is accessible to us or not, and then step by step debugging our way through. We'll run the test case that we have on the kit, and we'll make it work there. Okay, but before that, let's go through the changes that we need in the test bench. And for that, I'll also open some slides to explain what part of the, so basically I'll open the test bench architecture and then go through block by block, which parts of the architecture will remain same and which parts will be done differently for our embedded UVM test bench to run on the SoC FPGA. And therefore, what we are actually doing is we are testing whether the design actually works on the FPGA, whether all the test cases pass or not. So in one way, this is running the test benches. So this is kind of handoff criteria. In the other way, you can also visualize it as a mini emulation platform for running the test cases quickly. All right. So let's go through the stuff first on the slides, and then we'll come back to the test benches that we make in the code. Okay. So let me pull up the slides first. So I need day 3 slides. Yes, I need day 3 slides. All right. And I go to the last slides towards the end. Yeah. So this is how it works with Verilog. There is a design under test, and then we give some stimulus to it. We generate the stimulus and give it to the design, and we collect the stimulus towards the on the bus and give it to the monitor. We also collect the whatever should be whatever is the read data on the output. So basically, we are creating two kinds of transaction here: one for writing to the device in order to give data to the device. Then in the end, we are reading from the device in order to get the input. So though the bus is same, but this collector is basically collecting the read transactions and passing them on to the checker, and this one is collecting the write transactions. Okay, now, so this is how it happens in Verilog, and this is Avalon bus. Now this part, this driver and collector part, will be taken over by the kit, because we'll be writing to memory mapped device, and for us it will basically be like we are writing into a variable. Okay, so just like we assign a variable, we'll just say write into a memory address, and that's it. And the stimulus generation, I mean the BFM part, and the so BFM part on both the sides, it's kind of taken care by the hardware itself. So it's as if the BFM is synthesized. So okay, in case you are working with a commercial commercial emulation platform, then also BFM is synthesized. So you basically are sending the data to the emulator, and the emulator, because this part is already synthesized, so emulator just takes the raw data in. So for our case, there won't be any driver or any collector. We'll directly be moving to the monitor, and we will have the AVL transactions. And actually, since there is no driver, what we'll do is in the virtual sequencer, we'll directly instead of having to transfer. Basically, this virtual sequencer is okay. Let me pull up the code, then only I'll be able to explain. So this let me say address. Okay. Okay. So first, we are okay. This is also important. By default, the name of the file in D language is the name of the module. So for our original test bench, since the test bench file was named avmm dot underscore sha3 dot d, the name of the module was avmm underscore sha3. Okay, so now there'll be slight confusion. I mean, this module system is D specific. Don't confuse it with Verilog modules. So D also has some construct called module, but it's a software module. It's not Verilog kind of module. So every file is by default a module, and the name of the module is same as the file name without the extension. Now for DE10, we are creating another test bench, because we need to modify it a little bit, because uh, our BFMs are synthesized now. So we call it we name it differently. We name it SHA3 underscore DE10. Okay. And this one is SHA3 without DE10. And since we want to still have the same module name, so we hardcode the module name on the top of the file. Okay. So now the file name will not be module name. Module name is different from the file name. Okay, so we want to do it because the type names will be, for example, if you are invoking this type, then the actual type name will be module name dot type name. It doesn't happen that way in system verilog. It's a system verilog. Every type is named just by the type name. Here it's the full type name, so module name dot type name. Okay, so that's why because when we are running with Verilog, this is the file used. When we are running with the kit, this is going to be the file that we'll be using. Okay, now with Verilog, we had a different file name, and that becomes the module name. With the kit, we have a different file name, so we override the module name by putting it explicitly on top of the file. All right. Now the other changes. So we actually import a lot of system level functions that we'll be using. So we'll be using So there'll be something related to virtual memory because we are using Linux, we are using an operating system. Every operating system will be using virtual memory. So I'll explain that concept a little bit later, what virtual memory is. But since we'll be using it, so we need to map hardware device using virtual memory. And then all these are required for mapping purpose. And then we will be using volatile load and volatile store because normal read and write into memory locations, they go through cache, and we want to avoid that. So in D language, you have to use functions for writing directly into memory locations. So though we are writing into virtual memory or reading from virtual memory, but this virtual memory is actually mapped to physical device on the FPGA, and we have implemented some registers on the FPGA. And since that's what is there, so we have to um, use different functions. We just can't assign value to that address. We have to use some function to store into it because we want to bypass the cache. All right. Otherwise, if you are connected the device through cache, then there'll be cache coherency issue because the device will have some data, and the cache doesn't get to know because we are accessing physical device instead of accessing RAM through the cache. The cache doesn't have a way to know that the value on the physical device has changed. So cache will think whatever I read the previous time from a particular address, it will be the same because cache doesn't know the physical device will be changing because just like memory, it will assume it won't change. Okay, so in memory, whatever you write, when you read back on the same address, it will read whatever you have written over here over that. So a cache is useful because memory access will otherwise be slow. Here we are accessing a physical device, and physical device needs to bypass the cache because physical device access is not slow, just like memory access is slow. Physical device access is not slow. First of all, that so there is no need for a cache, and then physical device is volatile. Volatile means it changes on its own. Memory is non-volatile because whatever you have put there, it remains there. A physical device uh, will will change its value depending on the state of the physical device, the hardware state of the physical device, and therefore, if we access it through cache, we'll get wrong value because the cache will interfere and it will assume that whatever was the value earlier, the same value would be there. Okay, so we import those functions as well, and then we have a new driver because this driver doesn't work at AVL at the Avalon layer. This driver works because we want to make the whole thing more compact, so and faster. So whenever we had an SHA3 sequence for very long, we had to break it into Avalon sequence items, and Avalon, that breaking process, that creation of new transactions, etc., is going to take time. So we want to make it more efficient, and therefore we will work at the SHA3 sequence level itself. Okay, so we will have that transformation of the original sequence into those frames. But after those frames are formed, we will directly play the SHA3 frames into the memory device memory locations. Okay, so just a way of making the simulation faster. Our aim is to provide the same stimulus to the design which is mapped on FPGA as we were providing in the Verilog simulation. So, and our aim is to make it work much faster. All right. So now, since we have a new driver, we are not using the driver at Avalon level. We are using the driver at SHA3 level itself. So we have a new connect phase, which connects the SHA3 sequencer to the driver. All right, and this is the new driver. So let's go through the code of the new driver. So the upper frame of Emacs, I'll expand that a little bit, and let's see. So I already explained why we have a new driver and why we need to connect it. Okay, now let's look at the driver. So this driver has analysis ports because we will be, as we drive data, this is a duplex driver again, because the driver is accessing any read or write operation that needs to happen on the bus interfacing with the FPGA. Okay, so any write as well as any read will go through the driver. Okay, so the driver, since it's a duplex driver, has analysis ports as well, and these analysis ports will get connected to the monitor, to the scoreboard. So there is a analysis port for request and there is a analysis port for response. And then whatever you see under Cyclone 5, this is something which can run only on the kit. It can't run on my machine because the kit will have access to the kit can access FPGA. My machine where I have this code can't access FPGA because there's no FPGA on my desktop. The FPGA is there only on the D10 Nano kit. So whatever you see inside version Cyclone 5, so this block of code, if I run this test bench on my server, then this part will not be run. This part will run only if I have the FPGA, because it will run only if I compile for Cyclone 5. Okay. Now therein, in that portion, I provide information on what my base address is for the device. Okay. Now this you need to remember because the same information we need to provide when we synthesize and when we create the bit file that would be matched to the FPGA. So then we need to have the same address. This is the physical address of the device. And then since we'll be writing or reading from multiple registers, we also provide a range. We have actually kept it much more than what we require because we have only one device. So, but we have to provide the span or the range of addresses that we will be using. We won't be using the whole range, but we'll be using a part of this range. Okay. Then, since all this gets mapped to virtual memory, so we need to have pointers to the virtual memory where this physical address range will get mapped to. And since everything in Linux, so I'm making a very generic statement, but this is a true statement. Every physical device in Linux is a file. Okay, every device is a file. So if you are accessing something through USB, it's a file. If you are accessing the hard disk, it's a file. If you are accessing something through the PCI bus, it's a file. And we are accessing this device from The FPGA, so it also needs to be opened like a file. Okay, so this is the file descriptor for the hardware, and then later on when we map registers, okay, so in the driver we'll also be opening the hardware and we'll map it to registers. So this is how it is happening. So the map registers is also, mostly it is getting executed only for, actually compiled also for Cyclone 5 only. It doesn't get compiled, this portion, if I'm running it on the server. Okay, so now I open the memory device in read write mode, in read and write mode, both RD and write, because I need to access the FPGA, some registers in read mode and some registers in read as well as write mode. So I provide that flag. This flag has to be given all the time, so I don't remember what it means. But whenever you are mapping registers on FPGA, you need to, all the time you need to give it like this if you are doing it in read or write mode. Okay, and then in case your memory map, you are not able to open it. For example, if you are trying to do it on a server instead of doing it on a kit, then you won't be able to open it unless um, you are having permission. Um, so basically, that will happen only if you are doing it as root, or you are having some information in the device tree which lets you do it. Okay, so once you open the memory, then you are mapping the memory to, so you are opening memory here and you're mapping the memory to virtual memory. Okay, so mmap command will do it, and normally it should happen without failing, but just covering uh, those corner cases where it might fail. For example, your virtual map doesn't have space for some reason, so it might fail. So that's when you want to execute this code and get over it. But normally this won't happen. So when we run it on the kit, this message won't happen. And this also won't happen. But those are the uh, failures, which failing scenarios, which we have to take care of. Okay. So once all this has happened, you get the virtual memory address in mem. Okay, and virtual memory address always is of type void pointer. And then you want to cast it into reds, because all our reds are, so void pointer, by the way, is works like when the pointer increments, it increments in by 1. So step is 1, because void pointer is byte, so 8-bit location. Okay, and then you want to cast it into integers, because all our registers are 32-bit. So after casting the pointer, you get reds, and it's the reds we'll be using for passing stimulus to the FPGA, and it's the red again we'll be using at slightly different location to get the response back from the FPGA. Okay, so this is the setup process. Every time a test case gets run, we will need to map the hardware to virtual memory. And once the test case is over, we want to undo that virtual memory mapping, because otherwise, every time we run a test case, some portion of the virtual memory will get mapped, and therefore the virtual memory keeps getting incrementally mapped. We want to avoid that, because we were using this part of the virtual memory only for this test case. So we use the final phase for the tear down sequence and we unmap the virtual memory that we have mapped earlier, and we close the file because we were accessing the device as a file. So we close the file descriptor, and that's what happens in the final phase. But the final phase again will be there only for Cyclone 5. In case we are running it on our server, all this doesn't make sense. So all this doesn't need to be executed. In the run phase, we will be mapping the registers. We could have had a separate phase for it. We could have done it in start of simulation phase just before the run phase. But this is where I have put it for now. Okay. And in the get and drive, we keep generating sequences, and we keep collating the response. So we generate a sequence. What is important is execution of the request and collation of the response. Okay, so let's go through these two functions. Execute request. Again, it all happens. Most of the code you see here, this is right away happening on the kit only. So we are creating those frames which are 200 byte long, and we are sending it to the kit. And when we send it, in the end, you see volatile store. So we are writing onto the FPGA. Okay, and then when looking at the response, we are using volatile load, and we do it on the address, which is, let me show you where these addresses are. So this is 300, and this one, when I'm doing store, I'm using the base address and base address plus 200 for all my stores which are sending data to the FPGA. And then in the end, I have to write to a couple of control registers. So let me relate it to the slides. So this is what I'm talking about. So all these frames need to be written into the block. Okay, and it's the state which is the output. So the output has to be read from the response has to be read from the state. Input has to be written into the block. But in addition, we also have some control registers, and these control registers are at address 20. So we don't need status or version, or all this is kind of fixed. We just need the control, and in the control, we will be putting 1 into init or 10 for next. So either we'll be saying 1 for the first frame, and for the next frames we'll be saying 10. So I either be putting 1 into it, or we'll be putting 2 into it. So if we compare it with our code, that's what we are doing. We are writing into either 200 or we are writing into 20. Okay, and when we are reading from 300. So we read the output from 300. We give the input at 200. Yeah, we give the input at 200. We read the output from 300, and we also give input into the control register, either 0 or 1, depending on what frame it is. And this is on address 20. So if we look at the code, whatever we are giving in, we are giving in at 200, which is a hex address, divided by 4. Why divide by 4? Because we are using pointers, and pointer arithmetic is word wise. So when we are accessing a register address. As a register address, since our word is 32-bit long, the pointer increments at a step of 4 instead of byte increment at a step of 1. It is word increment, and therefore it is at a step of 4. So we need to divide it by 4, and then whatever word we are reading or writing into this block. Okay, so that comes with I. The count is with I, and we put that word there. And after putting all these words into the block, we need to tell the design that it is either the first block, if we put 1 here, or it's the subsequent block, so subsequent blocks by putting 2 here. Okay, so corresponding to the spec, this is where we put the control signal, and the control signal has to be 1 or 2. 1 for init, 2 for next. So the first frame will be putting 1, and for the next frames we'll be putting 2. Okay, so as we do that, we'll also put 0 just following it, because this needs to be a pulse. So put 1 here and then say 0, because it needs to be a pulse. So basically we are giving it value 1 only for as a pulse for some time, and then we are taking it back to 0, and we are giving value 2 for some time and taking it back to 0. Okay, so this is how we are giving the input stimulus. And for reading the output, again we divide the output address, which happens to be at 0x0300. We divide it by 4 to convert it into word address instead of byte address, to take care of the pointer step, which will be 4. And so this is our base address. This is our offset to the base address. And since pointer arithmetic is word-wise, so we divide by 4. And this is our the particular word we are reading from the output. Okay, so then whatever we read, we convert it into data bytes, and the data bytes we collate into the response. And once the response is completely formed, we write it into the monitor. All right, so this is our monitor logic now. Collate response, the lower level monitor logic, and after that it is sent to the higher level monitor port. And this is our driver logic. It's implemented as a function instead now, because we are interfacing at software level rather than having a BFM. So then we have I need to expand this. So this is what will happen. We are comparing against our Verilog test bench. So then we have this component, which is the scoreboard, and it works slightly differently, because instead of having, in case of Verilog, we just had one monitor, and all the transactions used to come on that one monitor. So we just had this monitor because we are playing transactions here and we are reading back here as well. So all the transactions get collected in one place. I'll show you that code in the BFM. And this is how it is done. So this is only virtual in the sense that it actually doesn't exist in the code. So, but we are trying to point out that there is a collector. The collector works for read as well as write, input as well as output transactions. Output transactions will be read transactions, and input transactions will be write transactions. So we just have created one monitor, and it has both kinds of transactions. Just that in the type of the transaction, the monitor puts whether it's a read or write transaction. Okay, and we send it through the same port in a Verilog test bench. The test bench we interface with Verilog. We send it to the same port of the monitor in our FPGA test bench. We actually have two ports. So in FPGA, what we are doing is we are writing request and writing response separately. Okay, but the rest of the logic is same. We will say matched or unmatched. So we will have the response, and the response will be, so the request which is coming through a different port is stored into one place. We call this variable SHA3 request. And when the response comes, we apply SHA3, which is the reference model, on the request, and we get the output from the software, the reference model which is implemented in C, the SHA3, SHA3 algorithm that we access on the top here. Yeah, this is implemented in C. Okay, so this one, the same way as we did for Verilog, we apply it on the input to get the output. We apply it on the input to get the output, the expected output, and then the expected output is matched against the output that we actually receive. And then we should get either matched or unmatched. All right, so this is how the scoreboard works. And the only important thing is we should be able to replicate the stimulus. Whatever stimulus we were able to run on the Verilog simulation, the same stimulus we should be able to run. So though the architecture of the test bench has changed, but the stimulus should remain same. Okay, and that is important because that's important for emulation as well as for the other use case which is the handoff use case. Because if something fails on the FPGA, there has to be a way. So something failed in the FPGA. In case we are using emulation, we are using the FPGA for emulation, and something failed, then debugging on FPGA is more tough. There are ways to debug it on FPGA, but they are pretty tough. So we want to take the failing test case back to Verilog and run it there. Okay. The point is we'll be able to run many more test cases in emulation platform, and say if we are running 100 test cases and out of them one failed, then we know about very quickly we know about that 100 are passing. These 100 test cases in Verilog simulation may have taken days, and here similar number of test cases may take 1 hour. And if one of them fails, we take it back to simulation because simulation is easier. All right, easier to debug. All right, so we go ahead and find out the other differences. In our DE10 test bench, there's no agent for because there was the agent for lower level stuff. That one is not there. We have directly instantiated the monitor. There is one level of monitor will be absent, and the other one we have in another place. Okay, And some connections will be different because the architecture of the test bench has changed. And this AVL agent is not even defined because we are not working at the level of AVL. AVL is taken care of. It's synthesized. The Avalon part is synthesized, and we access the synthesized part. Then finally, we have the test case, the parameterized test case. It's there at both the places, but it's slightly different because in Verilog we were running the sequencer for read and write. Here we don't actually have a sequencer at that level. Okay, so basically, uh, just to tell you, there is SHA3 sequence which needs to be run. Here we have, in addition to SHA3, we have um, the write sequence. So these are the AVL sequences, the virtual sequencer, which needs to be run. Those sequences also need to be initiated. But here we just have the SHA3 sequence. This is the only sequence we have over here. Okay, and we put the sequencer there. We start the sequence, and we do it 1,000 times. We need to the only thing we need to copy from here is this part. Yeah. Okay, so yeah, we need to see randomize it as well. So this is how you do it, and then the the one which you had for the one which we had for Verilog, we had created another test case. Remember, we did that before we tried factory overrides. So the same stuff we are doing with factory overrides. So I can add the. So this was to explain how complicated things would be if factory override was not there. So I'll comment it out. Okay. Now in Verilog, since Verilog will be invoking the test bench through PLI, we were doing it inside initialize ESDL function, and we were initializing the test bench. The same thing we'll do on for our test kit or for our FPGA board in the main function. Okay, and here we did it in background because we wanted to give back the control to the Verilog simulation. So this test bench will run on a separate thread. Here we are not doing it in background. So so this main function will only end. Here this function would start the test bench in background and will give the control back to the Verilog simulation because we are running the simulation on a different thread. Here we run the main function. We keep the control to ourselves because there's no Verilog running in parallel. So we don't need to do it in on a different thread because there's nothing happening in simulation in Verilog simulation. We just have the test bench running. Okay. So some other things here during elaboration, I'm also putting args. Okay, because I need to get the command line arguments from the main function. because I need to specify the name of the test, whether what kind of verbosity needs to be there and other stuff. All that goes through the command line arguments. So in case you are using the test case on the kit, it will be an executable. It won't be a library. And there you get it from the main function. Here you get it from all those arguments will be passed by Verilog. And then we have, under the hood, another way of getting the arguments that got passed at the Verilog command line. We get it from via PLI through whatever was given to the simulator. We get it from there. In the test bench that will run on the kit, we'll have to manage it ourselves. So we pass it on to the test bench like this. Okay, and then there is something to the seed. We'll talk about it later. And then since this, so the seed, in case the stimulus has to be same, it has to be same. With a different seed, stimulus will be different. Okay, and then in Verilog, we are setting the test bench in VPI mode because there needs to be synchronization with the running Verilog simulation. Here it is in async mode because there doesn't need to be, nothing else is running. So we don't need to synchronize the test bench with anything else. All right. So having done that much, so this is just like PB here, test here, doesn't make a difference because it's just the name of a variable. And having done that much, we should be able to run this test case on the kit. But before we do that, we'll run this test case on the server itself as a standalone executable. There is not going to be any reads or writes into the FPGA. So there won't be any response to the scoreboard. There won't be any matching or mismatch kind of uh, uh, messages coming, but nevertheless the stimulus will be generated. Okay, and when we compile it and run it, so one change in the test bench was we are uh, instead of doing it for over here somewhere. Where is that? Just let me search. Yeah. So instead of doing the 100 sequences, we'll be doing 10,000 sequences because there's no Verilog simulation. So we are going to have many more sequences running uh, in a little time because it runs very fast. There's no Verilog simulation to interface with. Okay, so so let's make it 100 only in the beginning and then we'll modify it. Okay, so what I'll do is I'll exit Emacs and I'll come to the home. I'll come to my terminal. Okay, so here I am. If I say make, so it is making my, so first it's creating the test bench for the simulation, and it will also create the test bench for which runs independently of simulation. So now it's creating a standalone executable. The name of the executable is going to be AVMM SHA3 underscore DE10, but it's actually X64, so AMD64 binary, okay, which is standalone, and we'll be able to execute it on our normal desktop because we compiled it for X64 only, AMD64 only. And so these are the two files that got created. This is my shared executable, which gets attached to the simulation. This is my test bench, which will run standalone. Okay, so let's first say make run. Make run will run it for Verilog. And since we are not dumping uh, transactions into the log file, so I'm just running it without those messages. Okay, so now if I say make minus n run, it will give me the arguments that I was giving here. So this is what the command line arguments. So this is required by Keras Verilog. These are the command line arguments here to here. All right. So now the same arguments I need to give to my standalone executable. This is my standalone executable, and I give the same arguments. Actually, this is commented, so it doesn't make any sense. So this one. Okay, it ran very fast because there was no simulation running. But instead of none, if we give medium, we will see those go up. Sorry, always get confused because I'm generally use a Linux machine and this is over Windows. So you get all those sequence items getting generated and randomized. So 100 sequences, but it happens very fast because there's nothing, there's no Verilog simulation to give it to and get a response from. So we see most of the time was going there. All right. So we get the same, we get to run the same test case this fast. And if we don't give medium, then we'll see how fast it is actually this fast. Okay. Now I'm going to change the test case and I'm going to put in, instead of 100, I'm going to put in 10,000 over there. And still it will be very fast. So instead of 100, I make it 10,000. Okay. And then I compile again, make. Okay, so I have compiled. So now there are 1,000 transactions which are coming in. So let me run and 10,000 transactions. So now it's taking some time because there are 10,000 transactions to take care of. But comparatively, it still took less time than the one which was running with simulation. So the one with simulation was kind of taking about 15 to, depending on like how much loaded your server is. It was taking about 15 seconds. And this one is taking time. So this one is taking about 3 seconds, 3 to 4 seconds. But these are 10,000 transactions. So you can see like a median here, those transactions will get dumped. So since that dumping is happening, it will take more time. I don't know how it will be looking at your end because my terminal is scrolling very fast. I don't think WebEx would be transferring images that fast. So, but the scroll is happening very fast. So it takes quite a bit more time because of all this dumping on the log file. And this is precisely why, in Embedded UVM, we have also implemented lazy log reports. So in case log reports are not getting dumped, things become much faster. So that's a feature which makes embedded UVM very fast on emulation platforms or on embedded kits. Because if you are not dumping, then the string which needs to be dumped is not even constructed. So system Verilog constructs it even if you are not displaying it. The construction happens anyway. So because of this log, because of this log getting generated, it's taking much more time because of the verbosity level. So we can see in the end there are 10,004 UVM info messages. So there is one message for each of the uh, transaction or each of the sequence item, SHH sequence actually. So if we say none, it happens in simply in 4 seconds, and there are only 2 UVM info. And in case you dump all those messages, since the messages, each of the message will have UVM info, so those get counted, and that way. Okay, now the interesting part is we have pretty much the same UVM which will be running on the kit, and when we do that, we'll be able to override the set type override equal to AVMM SHP dot sequence SHP sorry dot SHP sequence item comma the same thing with request 0 request 1 whatever or empty for that matter. So let's say request 0. So now you will see those messages. Sorry, so something. Okay, because in uh, the test bench we had here, so we need to modify that. We need to include these sequences. So let me do that. So on the top, we need to have these extra sequences. So empty is there, remainder there, it is there. So why it will take? It said error cannot resolve override or original type is because the override type is not registered with factory. I need to check what's happening there. So the factory information gets info request 0. Oh, actually I had a typo. It's not request 0, it's remainder 0. Okay. So the same way, all the factory overrides, everything will be possible on the kit itself because it's the embedded UVM which is providing all this functionality, and the same library will be using with Verilog as well as with the FPGA. Okay, so we ran it with uh, the same one with remainder 0 or remainder 1, and then it's actually taking much more time because probably the stimulus is much bigger now because because of the size of because of the length of the trace becoming different. All right. Now one small change will be required here because it's not printing the factory information. So I'll make that change. So edit dot test bench, and there I'm printing the factory information. Factory get print the base of the test. Okay. So this was missing in the test bench file over here. So there is this one, the one phase. So just add this line. But so it's here. After I have put the train time, there's no train time also over here because we are running it on the kit, so we don't need a train time. And factory get print before I create the sequence. All right. So this drain time, I hadn't explained it earlier. So drain time basically means when I drop the objection, after that, when I give that statement of dropping the objection, like I'm giving here, after that for 1 microsecond, it will remain there. So the actual dropping will happen only after 1 microsecond of me dropping it. So I wanted to give drain time over here so that because this is the input stimulus, so I want to give drain time so that my DUT, whatever transactions are going in, it's able to crunch those and give the output so that the output to the input sequence also gets registered. Okay, so that's why some drain time is provided here. That's what drain time does. So on the kit, drain time doesn't make anything. If you look at the kit, or actually the standalone test case right now because it's not running on the kit yet. So the simulation actually is running in 0 time because so you see this last message, this is coming at 0 time. So everything runs at, there's no simulation time, everything is 0 because we are not running the actual design, we are running it on FPGA, and FPGA is not a simulation, it's the actual circuit getting stimulated. So there is no concept of simulation time. Everything therefore is 0. Okay. So I compile once more because I added that one line. Okay. So there's only 15 minutes to break. So what we'll do is rather than going for the next step, I'll want to have question answer session right now, and then after the break we can start with the rest of the stuff, setting up the kit. I'll actually be sharing the video as I set up. What are the different components and how I set them up. So all that I'll be sharing on the video, and then I'll compile the test bench for the kit, transfer it to the kit, and before that we need to um, even go through the synthesis of the block on Quartus and then creating all the files. It's a good amount of process we have to go through yet. So, but since that can't finish in 15 minutes, so what I'll do is I'll have a question answer session, and at the end of the question answer session, we can have a break, and then once we come back from the break, I'll show you how the whole thing is set up. All right. So I stop sharing, and you can put your questions in the question answer tab, and I'll try to answer as many as possible. Okay, so there are already questions. We have to download both the files in EUVM directory. You can download them anywhere. Just that remember to run the setup.sh after untarring, so it will set up the files so that you don't get into any issues compiling and linking. So you won't have to set the LD library path and do stuff like that if you set up. Can I watch through YouTube? Will my attendance be considered? Because in YouTube, we can rewind also, and it helps us to clear some of the concepts. So you need to talk it out with Firozaji. There has to be some way to find out whether you are there or not, and that can't happen on YouTube because we don't know who all is watching on YouTube. So you must at least log on into WebEx, and then parallelly you can watch on YouTube. So that's what I can suggest. So that I agree. Since WebEx is live streaming, so there'll be bandwidth issues, and you'll get to miss on some part of the thing because of bandwidth issues. On YouTube, you can play it again, and at least at the most it will buffer up and then show it to you. So but you won't miss anything. Okay, so then Umang is also saying he doesn't have data to log on into both the places. I would suggest log in into both the places, but on WebEx, maybe I don't know how to go about it, but maybe you can switch off the video so that the live streaming doesn't happen. But I don't know whether that's possible. Okay. Firozaji?
Yes, sir. Good afternoon, sir.
So there's somebody who is asking, like he says he doesn't have bandwidth to open WebEx as well as to open YouTube, and WebEx has issues because it's live streaming, so therefore he doesn't get the live stream properly. So he wants to do it on YouTube, and so he is asking how the attendance will be marked.
Sir, actually, the thing is that the live streaming of the WebEx is not going to affect the concerned person data. So this, I will say that it has not been affected. And right now, so I will request him to please connect to the WebEx. Don't go with the YouTube live streaming. Once the session is over, you want to revise in the YouTube, you will be getting all the videos are already uploaded from day one till today. So you
Okay,
can
but
always refer to
what
the
his
video.
concern is if he's going to watch on WebEx, then say he has 1 GB quota for the day, then his
Hmm.
quota is already finished, and in the evening he can't watch YouTube.
So because YouTube, we don't have any mechanism to track the attendance. You
Yeah.
to understand, like,
Yeah.
please try to understand because YouTube, we cannot track the attendance.
Okay. So
So,
yeah, maybe you can watch the video later, but
yeah.
for now you need to be on WebEx for the attendance to be marked. Then there is a question from José. He's asking, sir, please, so you please open the file dev.mem. What that you have generate using file descriptor. Actually, dev.mem is the standard file in some devices like in Cyclone 5, or it may be the operating system which is doing that. The all the peripherals or all the devices, hardware devices, are mapped to the same memory bus as the main memory. So you open the main memory and then you get the file descriptor, and then you map the memory to for the particular hardware. So that's what you do. In some other devices I have seen, so there is a separate memory space for what you call universal IO. So there is a UIO space. So instead of opening /dev/mem, you will be opening /mem/uio. So, but it doesn't really make difference in the end because you have a lot of virtual memory and you won't be using all the space. And just to answer your question, we open the dev mem because we are modifying the virtual memory space, and we want to add the hardware device to the virtual memory space. Why we are not using Avalon bus in FPGA test bench? Because as I said, the Avalon part of the test bench, which is the BFM, is synthesized. Okay, so it's already on the FPGA itself. So basically, when the processor is reading or writing anything into the hardware, the driver part of the BFM, which we used to have in the test bench, that is already on the FPGA itself. So that is also synthesized along with the design. Okay, so this will happen with the other emulation platforms as well. The BFM gets synthesized, and that's how emulation becomes faster as well. Because BFM is not, if you look at it objectively, BFM converts a transaction into signals. And if we work at signal level, the whole thing will become very slow because we are then controlling at bit level everywhere. Every bit has to be taken care of. So we want to keep our, so even if there is no DUT, because the DUT has been mapped onto the FPGA, so still test bench is having a discrete event simulator, and that simulator, we want to make it work at transaction level, and that too preferably where the transactions are bigger, like the sequence instead of sequence item. Okay, so after that, breaking the sequence into sequence items and all that stuff, and then having a driver at the Avalon level, we want to forego because we want to make the test bench work as fast as possible because test bench is the bottleneck now. FPGA works almost at zero runtime. So FPGA doesn't take any time to respond to your data. It's the test bench which is taking time in execution, and we want it to work as fast as possible because we want to run the test cases as fast as possible. That's the idea of emulation, to make the test cases run faster. So since in simulation, your Verilog simulation will be your bottleneck. So in simulation, the test bench is not the bottleneck, it's the simulation which is the bottleneck. And that's why, since the simulation anyway is running at signal level, in the test bench, you will have to kind of convert your transaction level or TLM level transaction using BFM to interface to the to the DUT via signal level. In emulation, you don't have to do that because the BFM is synthesized, and that's one of the things which makes emulation faster. Okay, and then there is a question from Tosif who is asking, without using create method, how you did the factory override by just calling the constructor using new method only. So I think because of WebEx or whatever, there's some miscommunication here. Actually, I wanted to show that if you are calling constructor directly, even if you do factory override, uh, the factory override will not get affected because you are not using factory to create the transaction. Factory override will become effective only if you are using factory for creation. So just to demonstrate that, I created a sequence using the constructor directly, And I demonstrated that even if we override the factory, it's not making a difference to the sequence. However, how our reference block, but in our case, scoreboard mimicking the behavior of DUT. Okay, so basically you are saying the scoreboard is having a reference, basically the functional, the reference model of the DUT, and therefore in the scoreboard we are able to get, given the input stimulus, we are able to uh, create the expected output and match it against whatever we get from the DUT. So you are asking how we are able to do it, how the self-checking of our test bench is going on. So let me answer the other questions, because for this I'll have to go back to the code and show you how it works in the test bench actually. So let me answer the other questions. In the code, you have used cast. Please explain this. So I have used cast at multiple places. I have used cast for uh, for various. So again, I'll go back to the code and say it. We are not getting display of presenter. So that's something you need to work out with Firozaji, why that is happening. Then you have a question from Yash, and he's asking if we are not using iVerilog for FPGA test bench, then where it is running. If it is running on FPGA board, then can you explain once again briefly that how our test bench is connected to FPGA? Okay, I'll take this question and I'll take it on the code itself. Sir, can you give in writing the steps followed, since I find it difficult to follow. So I made some progress today, but I only ended up giving as much as how to install the thing. So I'll for each example I'll give the steps on the forum, and then we can take it from there. Okay, then there is the last question. Where can we get this new FPGA test bench? I'll be once I want to, though I had done this exercise earlier on my own, but I want to do it with you people today. So after I'm done, I will be checking it into GitHub so that you people are able to run it at your end. Okay, before I go back to the code, I'll just switch on my camera and I'll show you the board. Okay, so this is the board. Okay, so this is the board we'll be experimenting with. You hope you are able to see the video. There is some light blinking out there, which basically means basically the FPGA is responsible for blinking that light. It's not the, like, if you buy the 10 nano, then you get it without the box that I have put it in. This box you can talk to me separately. If you're buying a board, then you can talk to me separately how to create such a box, because the board otherwise is sensitive to your hands. So this one I can handle anywhere, because I'm not I won't be touching the board. I'm just touching the fabricated cover, and the fabricated cover also has a fan on it, because when we run test cases on Cyclone 5, if we run test cases for long hours, it has a tendency to heat up, and if it heats up, it can either shut down itself. Probably it will shut down itself, but you can't rely on the shutting down mechanism. So you don't want to, just like if your laptop heats up, and it should shut down, but in some cases the heat up is so much that it doesn't shut down. It basically gets the processor is destroyed, gets burnt up. So the same way, I want to put a fan here just to avoid heating up, and just to be able to run test cases if I want to for long hours. The back side of the board, somewhere here you see a slot wherein I have put a micro SD card, and this is the hard disk of the board. This is where the operating system gets picked up. This is also where it picks up the design file for the FPGA and the rest of the configuration. So I'll talk about it in the afternoon in more details. But for now, I will share my screen again. So there are a couple of questions that I need to handle. One of the questions is about how the test bench is getting connected to FPGA, because we are not no longer running iVerilog. And the other question is uh, where casting. I need to explain casting, how and when I'm using casting and what it is doing. And then there is a question on reference block or the reference model and how that reference model is giving me the expected value. Okay, so these three questions, one about casting, the other about reference model, and the third about how the interface between FPGA and the design and the test bench is happening. So just now, there is a new question. Complete design can be tested using test bench. Yes, in the sense that's what. So basically, we are mapping the design onto the FPGA, and then the test bench will be running on the processor, which interfaces with the FPGA. We'll do it in afternoon. I don't know whether we'll be able to complete that exercise today, because I'll also go through the other steps, preparing the operating system, synthesizing the design, and I need to explain a lot there. So then in the end, we'll be running it on the FPGA. Okay. Uh, then yeah, so basically it basically depends on the size of the FPGA. Cyclone 5 has big enough FPGA, at least this kit, it is having big enough FPGA which can take SHA3, and actually it doesn't even fill. I think it just fills 1/4 of the FPGA. So we could have bigger designs getting, which we can test using this kit. But then there are very big FPGA, SoC FPGAs available, especially from Intel, where you can literally put in almost a billion, if not billion, 100 million gate designs. Okay, so yeah, so just to go back to our questions, wherein I need to show you the code. So first, let me share the screen. Okay, now if you look at, so I'll open Emacs here. Okay, so let me take all the three questions one by one. The first question is about casting and why, and what casting is about, and why we need it. So let me go to the test bench directory, and here, so if you look at um, the test bench, the UVM test bench, which works with iVerilog, there could be some casting here as well. So here, for example, so I'm casting, okay, and then here also I'm casting. Here again I'm casting, cast. This also is a cast, okay, and finally here as well, there is a little bit of casting happening. This is actually happening in the scoreboard, no, in the right sequence, in kind of in the scoreboard only when I'm collating whatever I'm getting in the input. So I'm using low-level C function, C kind of way of doing it just to make it faster. Okay, and then you have a cast here. So there are a lot of casts at various places. So let me explain each one of them. The first cast over here, I explained you earlier why we take one object and we keep randomizing it, and after we randomize it, we clone it. I explained it earlier because if we create an object and after that randomize it and send it, and then next time we are randomizing another object. Okay, so that is one way of doing it. The other way which I am doing and which is the correct way is to just have one object and you keep randomizing it again and again. And when you want to send something to the sequence, to the driver or to the virtual sequencer, you do it by way of cloning. Okay, so this is the correct way because this way it will be much more runtime efficient, because if you randomize a new object, and since we are doing multi-core and stuff like that, then there is a new randomization engine which needs to be set up for the new object. Okay, every object will have its own randomization engine. So that is that initialization will take some time. It's also true for system where, depends on your compiler, but in most of the places, what will happen is if you create a new object and randomize it, and some sort of initialization will take, for sake of randomization, will take place on that object. Some memory allocation, etc., will happen, and your simulation will become slower. So that's besides the point. Why do I need to cast after that? I need to cast after that because the clone function is a base class function. It's going to return me base class. It's going to return me base class, in this case is UVM sequence item. And actually, the clone function works at a lower level, actually at a much more abstract class level. So clone function is going to return me UVM object, and that UVM object is the base class type unless I cast it to my own type. So request over here is SHA3 sequence item. So to convert it into SHA3 sequence item, I need to cast. Okay, so this is one basic uh, part of polymorphism. The actual object is not of the base type. The actual object in the memory is of this type only. But since clone method returns UVM object, which is the base class type. Okay, so we need to cast it so that we actually have this type available to us. Okay, so you probably in a 10-day workshop. I'm sorry, like I couldn't go through those fundamental details of how this thing happens, and let me see if I can take up this part on tomorrow if possible. But we need to understand how runtime objects can have a dynamic type, in that sense that the type is known only at the runtime, and then we can cast it to that, or so there is downcasting and upcasting. So I'll try to take it tomorrow because it's an important topic. But again, it's a workshop, which basically means that it gets you started, and that's why we are sharing code, and you can look at this code and or try to know the fundamentals yourself, try to research on web and all. But I'll try to cover this topic tomorrow. Then the other casts over here are simple casts. See, length is sometimes 64-bit because we are working on a 64-bit processor. And the result of all this is going to be U-long, because we are having a U-long data over here, 64-bit data over here. And this result is going to be U-long, and num frames is U-int. And since unlike Verilog, where if I am assigning a 64-bit value into 32-bit value, Verilog will not give me warning or error. Instead of doing it like that, um, embedded UVM and the base language, which is D language, it doesn't allow it. So you have to do explicit casting. So that don't do it inadvertently and thereby introduce bugs in your program. So this is intentional. So cast means you know that some information loss is taking place. You are converting a 64-bit number into a 32-bit number. So by way of casting, you can't, if you remove this cast, D language will not allow it. Then it will give you an error at this line. So let's for example try this. So now if I compile, it will give me an error. So error cannot implicitly convert expression which is of type ulong into uint. Okay, because you are actually losing information 64-bit to 32-bit, and D wants to do it in such a way that when you are taking this step, then there is, it forces you to make it explicit. So you will put this and you will know that okay, you are doing this, and that time while doing it you will also think whether this is safe or not. Okay, so I know my length is never going to be more than 32-bit length. I mean, 2 raised to a 32, that's a big number. So I know my data is never going to be, the array is never going to be that size. So therefore, this casting is safe and I'll do it. So this is that kind of casting. Actually, even in C language or C++ language, this feature will be there in the latest compilers. So it will, so you can tell the compiler whether, so probably it's kind of optional that it will give you a warning or error for such assignments. But in Verilog, it will simply do it without giving you an error or warning, which is basically very bad because there are so many errors, so many bugs which get introduced because of such assignments in software as well as in hardware. Same here, we are casting because we are doing an operation which results in more than 32 bits and we want to put it in 32 bits. So then this casting over here is because I get a number from some place and I want to cast it into an enum. Okay, so I can't assign that number into an enum just like that. I have to cast it. So this one is special. This one is pointer casting. So you have data, and that data here I want, basically data is coming probably in words, and then I want to convert it into bytes. So there's a word array, word level array, and I want to convert it into an array of bytes. So I'll do casting. Okay, so that I can access bytes inside an integer, and I can pack it accordingly into my array. So this is again some detail out there. Then there is another casting which happens in the test bench, which we'll be using on the kit. So you have cast here. This is similar cast. Okay. Now this cast is where you are accessing the hardware. Normally, when you access a device and you map it using mmap operation, which is a very low level operation in Linux, it's a kernel operation. Kind of, it makes a kernel call to make the hardware accessible to us as virtual memory address. So once you do it, you get a void pointer. So if you say meta x man, and then you say mmap. So mmap returns a void pointer. Okay. Now you know, because it will return a void pointer because it doesn't know what kind of physical device or physical space you are trying to access. Okay, now you know it that my device is on a 32-bit bus. So you want to then cast it into uint pointer. Uint is 32-bit. So it could be int pointer or uint pointer, doesn't matter that much because both are 32-bit, unsigned or otherwise. So you cast it and now you get a 32-bit pointer. So red becomes a uint pointer. Though it's actually the same value, but it's 32-bit pointer now instead of void pointer. So pointer is an address. So if you print mem will give you some location in the virtual memory, but that is kind of for sake of bookkeeping or for sake of compiling. That memory is void pointer. Uh, that means it's an abstract pointer which the software doesn't know about what kind of variables it's pointing to. But then you want to cast it so that because you know it's pointing to register reads and writes, and those registers are 32-bit. Okay, so that way. So that's about casting. There are two questions now. One is about the reference model. So the reference model, I didn't talk too much about it because it's implemented in C, and I picked it from the web. Okay, so if you look inside the test bench, then there is tiny SHA3. If you go inside tiny SHA3, you get a README which tells you what kind of implementation it is. So it is software implementation of SHA3, and so it gives you where to pick up the spec from. It has some notes on how it is implemented, and then you have C and .h file. I showed you these files earlier as well. Now these files have a software implementation of SHA3, and the main function which we need to call to access this implementation is this. Okay, so it takes in over here. So it takes in your SHA3 phrase, and since it's C, so there are no dynamic arrays. So it takes a pointer and the length of the pointer, length of the array from where the arrays. So this is where the array starts at. It's a pointer, and this is the length of the array. So you are passing an array to it, and then you are getting an array back from it, right? So that's how you um, have this reference model implemented. So I haven't even tried to understand, I haven't even made a try to understand how this software works because it's not my idea to learn what SHA3 algorithm is about. It's my idea of this workshop is to teach you test benching, and reference model is domain specific, so we leave it at that. So somebody who is interested in SHA3 specifically will learn how this implementation is, but for us it's important how to integrate it into the test bench. Okay, so that's what I'll cover now, and I had covered it earlier also, but I'll since there is some confusion somewhere, so I'll take that up again, and I'll open it. So this is the same signature that I have put here, SHA3. Again, input here and output coming from here. So the pointers, we are using pointers to pass arrays and to get back arrays. Okay. Now, when you call this SHA3 function in the scoreboard, you're calling it here. So you're passing your phrase, whatever randomized phrase Okay, whatever input stimulus that you have monitored, and then after monitoring, you again created a phrase out of it, and you pass that pointer, because that's what SHA3 as a function likes to have. So it likes to have a pointer and the length of the phrase separately, because the function is implemented in C. So though I have a dynamic array, I need to get the pointer out of it and the length of it to pass it to C. And since I need the result to come back, so I again have a dynamic array, and I set its length to whatever length is expected at the output. So I set it to that much length, and I pass this array pointer and expected length to the C function. So the C function will crunch data. It gets at this pointer up to this length, and it will create an output and put that output into the expected array. Okay, so this is where I am integrating uh, a checker reference model into my test bench. Okay, so that's to answer the second question. So there was a question on casting. There was a question on this, and then there was a question on how are we integrating, how are we passing data from the test bench to the FPGA. Okay, so let me do something. Okay, I'll actually open the code first. So wherever you see Cyclone 5, this is the code which will get compiled only on Cyclone 5. And when I'm running this code on my machine right now, since I'm not running it on Cyclone 5, this part is not running. Okay, I explained it earlier as well. Now, this part out here, because it's Cyclone 5 specific, is the part via volatile store. It's accessing a physical device, and that physical device happens to be the FPGA. And it's accessing this space on the physical device, this space. So FPGA on our Cyclone 5 system is connected via Avalon bus, and this is the address decoder. This is how my address decoding has been fixed for for accessing this FPGA device. We'll see it more clearly in the afternoon when we start synthesizing our design. Okay, so we'll see explicitly where we mention this address, that okay, this is where my design has to be uh, physically mapped to. Okay, and since there is a range of addresses, looking back at this, since there is a range of addresses, the address range starts from 0, and there are some addresses which are used here, and then there are some addresses which are used, address blocks which are used here. So we are kind of we need address space till 400, 0x400. Okay, since there is a range of addresses that we need to access, we put that in code as well. And since we are just going to use SHA3, there is nothing more. So I have given more space here. So it doesn't really matter. We'll be using only up to 400, but I have kind of booked more space in the virtual memory. Okay, because there's a lot of space available. I've just booked some space, and it is more than what I needed, but I have booked it. Okay, so this is where all my reads and writes from software are going to get, in terms of transactions, this is where the transactions are going to take place on these addresses. So it will become more clear in the afternoon when we see the block diagram in quarters, and we see how the things are connecting, and how when so the processor is the master, and this is only the software which runs on the master, and how the Avalon bus is getting connected to the master, and the master being the processor is just running instruction to read or write on these addresses, and how the Avalon bus actually takes that transaction, and the FPGA is actually responding to that transaction after that. Okay, so remember, all this is running on the processor finally, and the processor is accessing the FPGA by way of reads and writes. Okay, so, and then the question where somebody was asking if we don't have Icarus Verilog running. Of course, we don't have Icarus Verilog running, because Icarus Verilog was to run Verilog simulation of the design, and we don't have a Verilog design now. The design is already mapped onto the FPGA. So either we do a gate level simulation of the FPGA, and that will run very slow, and that's not what we want to do in the workshop. Instead, we want to run the test bench and access the mapped design on the FPGA. So actually, okay, let me show you another board. So just to clarify this part. Okay, I'm switching on the camera now. So see, this is another board. This is another board. Okay. So we don't cover this board in this workshop, but this is also some interesting experiment that we do. What we do is, this is a board which goes over Raspberry Pi as a hat. So it gets connected to the signals, the input-output signals of the Raspberry Pi. Okay, so you see all these connectors here in the bottom. These connectors out here, and this connector actually on the top. This is how it will get connected to Raspberry Pi. I'm not taking it out of the polythene I have here, envelope I have here, because I don't want to touch it with my bare hands. It might, it's like I need to keep it static, charge free. So, but you can clearly see the pins out here, which will get connected to the Raspberry Pi. So why I'm explaining this thing? Because the test bench, instead of instead of uh, giving the transactions or translating the transactions into and interfacing it with running Verilog simulation, the same data we could give through the input-output signals to the actual design. In an SoC FPGA, those signals are not getting visible to you, and that's why the confusion is there. Okay, but nevertheless, those signals are there inside the chip, and those get connected to the FPGA. And this, let me show you the device. This FPGA, this is a standalone FPGA. So Raspberry Pi, in this case, will have the processor, And then you have the processor getting connected to this FPGA, this chip out here, through this bus. Okay. Now, when we do it at this level, it becomes slower because the input output signals of the FPGA have to be accessed via an external bus, and that becomes very slow. Okay. If you have something on chip, it's faster because it has less capacitance on those pins. If it's outside chip, then there are pins which have a lot of capacitance, and you can't run signals very fast over there. So this is slow, but here just to show you how it will be done. The when we exercise the test bench, instead of having a BFM, and that BFM interfaces with Verilog and passes on the values to the Verilog simulation. Here we don't see the BFM because we are actually doing the read writes into memory locations. But ultimately in the hardware, you have those signals, and those signals will be integrating with the FPGA like this board will do with the Raspberry Pi, but it will be slow. On Cyclone 5, it will be very fast because it's inside the chip. Okay, so we are using a test bench and the software there. So in this case, when we do it with Raspberry Pi, you will actually be able to see the signals on oscilloscope. So you will be able to see. So in this case, when we do this experiment, since we have a limited number of pins available inside a chip, you'll have lots of connections. Outside a chip, a limited number of pins. So because the number of pins ports has limitations. So we'll be using streaming bus when we do here. And that streaming bus will be able to see on the oscilloscope. Okay, there it's Avalon MM bus, or you have an option to take AHB, Avalon MM, or AXI bus. But since it's inside chip, you won't be able to see the waveforms. But that doesn't matter so much if I'm able to run it so fast. Okay, so that's how the whole thing will work, and that's how, because it's emulation. Even with commercial emulation platforms like Veloce, etc., there's no Verilog simulation because the design is on the emulation board. If you want to do with a commercial emulation board or a platform, if you want to do a test bench in system Verilog, then if there is a system Verilog simulator, that simulator, that's a very different thing. Here we don't we are not using system Verilog, and we are using embedded UVM, and we are able to run, since it's embedded UVM, it has a very small memory footprint. We are able to run it on the embedded platform itself, and we are able to exercise the test the DUT stimulus in that way. Okay, so I hope it's clear. In case you still have questions, please ask, because it's very important that the fundamentals are clear before we actually start doing the stuff, so that you can visualize better and conceptualize better how the things are happening when we go through the process. So in case you still have questions, when we come back from lunch, ask those questions. I'd like to answer those first before we actually go in for our experiment, to our lab. Okay, so that's where I end, and it's already about what time it is. It is uh, 35. So let's say 40. So we come back at uh, 10 past 1, and then we will still handle the questions if there are any, because we have light stuff for tomorrow. QEMU will not take that much time, so there'll be we can, if there is a boil over, we can take some stuff tomorrow. So please ask questions when we come back, and we can take those up before I start the labs on the FPGA. And tomorrow we'll be covering QEMU. We'll also be, if and when, if there is some time left, we'll also cover a couple of other designs. And I'll try to cover this casting, upcasting, downcasting stuff that happens in C, C++, System Verilog, as well as in Java, as well as D language. So I'll cover these concepts as well. Okay, so 12:35 now. We come back at 10 past 1. And if you have questions, try to come back by 5 past 1. And then whatever questions are there, I'll try to handle those. So, okay, so we take a break.
Yeah. Yeah. Thank you, sir. Thank you, Puneet, sir. So please, participant, join us by, so what should we keep the time, like 1?
5 past 1, we come back. And
Okay.
then at 10 past by 10 past 1, if there are any questions, I'll start taking those. And then after that, we'll do the lab.
Yeah, sure. Okay. Thank you, sir. Thanks a lot. Yeah, hello, good afternoon, sir. So, should we start?
Yeah, good afternoon. I can start.
Yeah, please, sir.
So, how many people now?
140.
So, let's wait for 2-3 minutes for more people to join.
Yeah.
All right. So, there seems to be just one question right now. The question is how to include comment statements in each portion of the code during execution to know what it is executing. Okay, so usually, this kind of stuff you will do if you're writing C or Python code, and you are not using too many libraries, then usually you will be doing this stuff by including printf statements, which say where the where the execution is happening. Okay, now so I'll take this question in slight detail. In system Verilog UVM as well as in embedded UVM, because UVM is UVM, we do it via something called UVM info. Okay, because if you do it via printf kind of statements, then those statements you will have to comment out later on for the real code to run. Here, the UVM info kind of info statements, you may not comment out, you may just give a verbosity level here. For example, if I wanted to see if if my init pulse, how init pulse, whether the init pulse program is executing or not, or what time it is executing in the flow. So I can just write over here UVM info. Of course, if you are using system Verilog, then UVM info is a macro. So you will say tick UVM info, but here in embedded UVM, UVM info is a function. Okay. By the way, functions are much more preferred in today's world than macros. So because there's no preprocessor involved, so functions are so much more preferred. And then you will have a tag with UVM info. For example, my tag here could be debug SHA3. Okay, and then I may have any message over here. Say the message is at the start of init pulse. Okay, and then in the end there has to be verbosity level. So you will say something like UVM none. There are various verbosity levels starting from UVM none. You have UVM low, UVM medium, UVM high, and then finally you have UVM debug. So UVM none means this message will, debug is like only the when you want to debug, the debug messages will be printed. UVM none is uh, whatever your verbosity level is, the ones which are specified with UVM none, all those will get printed. So UVM none is like all the time, every time you want to run this test case, this will get printed. So instead of UVM none, you may give UVM debug, so that you want to print it only when you are debugging. So when your test case runs naturally without the debug mode, this will not get printed. So for example, I'll run this. So let me actually make it UVM none, so that it always gets printed. So what I'll do is come here and let me bring up my Emacs window, and here let me put UVM none. All right. So now if I compile it, so it's compiling the other one also because we made some changes there. Okay. Now if I say make run, something, I need to figure out why it's not printing. So when I say make minus run, minus n run, so this is the command. So my verbosity level is none. That means only the ones with none there could be printed. So let me change this verbosity level and make it low. Still it's not getting printed. So I need to find out why. Did I change the right file?
Excuse me, sir, you
Yeah.
are not sharing the screen, I think so.
Or sorry, I'll do it now.
Yeah.
Okay, now it is getting shared. So what I have done is at the start of init pulse, I have a UVM info message. It says at the start of init pulse. So unfortunately, I did it in the wrong file. So I did it in DE10 file. So that the one which is supposed to be for the board. Okay. So I need to do it in this test bench, and init pulse. So here I add that comment. So now when I compile it and run it again, Okay, so my compilation is done. So if I run it again, now I'll see those messages getting printed. Init pulse, init pulse. So this is kind of every sequence will have an init pulse, and that's where it is getting printed. Okay, now, so to answer that question, I hope I'm clear. Basically, when you want to, so the question was, can we somehow have some comments? So comments anyway can't be executed. So I hope that was, I got the right intent of the question. So when you say comment, then that means usually you use printf to find out the flow of the program, whether like when you're debugging, and then you comment those out. So in UVM, you will be adding UVM info commands, and then you will give none or some other verbosity tag with it. So probably like, for example, you could give debug, and then normally these won't get printed. Okay. And when you are debugging, then these get printed. So now it because the default verbosity level I'm keeping is none, so it won't get printed. But when I give in the run, I give verbosity level as debug, it will get printed. So it's not printing now. But if I give debug over here, then I'll see, anyway, debug is going to print a lot more messages as well, but I'll see those, at the start of init pulse, those ones will also be part of the log report. So now the thing is, let this finish. One way is I take a dump of this log report into a file and then look for whatever messages I need to look for. The other is I can grep through this log report and see if those messages are getting printed. This is also a third way. So let me show you the second way first. Third way, probably you will have to look at the reference manual, Union reference manual, but I'll give you the idea like how it happens. It's taking too much time because was it the log reports perhaps? Yeah, anyway, let it complete. Okay, meanwhile, I'll go through the Emacs and tell you something. For example, you want to just print the debug messages. Now, this part of the UVM info command, the first argument is called tag. Okay. Now, there is a way in which you can enable printing for particular tags. You may not enable for everything. So you can say just print the debug messages for this particular tag. So there'll be some configuration required, but you'll be able to handle that via the command line, and then you'll be able to print those. For now, what I'm going to do is I'm going to run it and use Linux to just get these messages. So I grep for these commands, these flags. So now you will see, because I used Linux, so you are able to see. And as part of UVM info, it also tells you where exactly this message is coming from and what time it is coming from. So all that also is available. All that info also is available. And actually the component which is generating, the name of the component is also given. Okay. So the message that you're giving, and in addition to that, you get the line number it is coming from, the time it is coming at, and as well as the comment that you are giving, that anyway is coming, the hierarchy of the component where it is originating from. So all that information is also available to you. Okay, so now I'll take a look. If there are more questions, I'll handle those questions. Otherwise, I'll explain the emulation platform that we are going to set up through a diagram, and then we will start the exercise. I don't think we'll be able to complete the exercise today because only 1 hour remains, but we'll at least cover the synthesis part because while doing it, I have to also explain you the various aspects of it. Okay, so we go to the slides, and I want to go to a particular portion of the slides. I these are, I think, day 3 slides. I need to go to day 1 slides. Okay, so let me open day 1 slides. Okay, yeah, so probably this one. Yeah, so let me open this up in Acro Reader. All right. So since there were questions regarding what's happening in emulation, so I'm opening this page of the slides. So see, this is a normal SOC, and as I told you earlier, only one portion of the SOC is application specific. The rest of the design is usually uh, peripherals, standard peripherals, or the subsystem, the processor subsystem, which is also standard. So usually that's what will happen on an SOC. In a normal SOC flow, for example, you have to verify everything because you may have bought Ethernet MAC from one vendor and the USB device from another vendor. Okay, and in many cases there'll be a USB subsystem and multiple USB devices. So you may have bought all this from multiple vendors, and you may have bought the APP and AXI bus bridge from another vendor, for example, and processor maybe coming from ARM or maybe from RISC-V or there are other possibilities. So now you need to find out whether your USB device works with the APP bridge, because there may be a lot of assumptions made by people who made the bridge, and there may be problems at the integration level. You may have misunderstood or you may have made a typo in your SoC integration, and maybe one of the signals is not connected, or there may be problems with the clock because there will be multiple clocks in a SoC like this. So there will be a separate clock for the memory controller because memories are generally slower than the processor. So there may be, if not for memory controller, for the external interfaces, there'll be separate different clocks and a separate set of clock for the peripherals. So all those intricacies will be there. And as a result, whenever you create an SOC, you have to go through a lot of verification. Now, my point of, I already told you all this. My point of talking about this now is once you integrate everything, you need to have an SOC level verification environment. So normally how it is done is, so you want to mimic the thing, you want to mimic the actual use case of the SOC. And in the actual use case, the processor is the master. And the processor initializes all the peripherals and the subsystem, the processor subsystem first. And after initializing, it starts, for example, it will tell USB to fetch data, okay, from a device, or it will tell USB to send out data on a particular USB channel. Okay, so now how you do it at SOC level is there are two ways. One is you will write your test case in C or C++ or assembly language. You will, and this will be bare metal C programming or bare metal C++ programming. So you can't use printf, for example, because your instructions are actually getting executed as part of the verification environment. So the binary file that you create from your bare metal programming will be loaded in the simulation model of the processor and it will get executed there. And as a result of whatever is getting executed here, there will be AXI and APP transactions. Okay, and as a result of that, in the simulation, there will be something getting written into the USB device. So that is SOC level verification. And since processor RTL, though the processor may not occupy a lot of area on your chip, but processor is some place where there is a lot of activity transaction or the instruction that goes to the processor needs to be loaded and then it's to be decoded and there will be a pipeline and a lot of stuff. So processor is full of activity and therefore RTL simulation of processor will take too much time. Therefore, instead of having RTL of the processor, you will have a model of the processor which will be written in C or C++, and that will integrate with the simulation via PLI, and that's how your SOC simulation will take place. So the so in a way, your processor is not RTL level simulation. It is some C++ model which executes your stimulus and then integrates to the AXI or to the APP bus via PLI. Okay, now this model will be provided by the same vendor who will provide you the processor core. And there is another reason he doesn't want to provide you with the RTL because RTL is his IP, and therefore he provides a model. And processors you usually get as either as hard macros, or in case they provide you RTL, you can synthesize it and create a processor layout. Okay, so now the point is, this is one way of running SOC simulation. The other is you will not have any processor and you will simulate the rest of the stuff. So you take out the processor from the DUT, and either you take it out or directly start controlling the AXI bus through force signals in Verilog. And thereby, though the processor is not writing anything over AXI or AHB bus, your stimulus is writing something directly over to the AXI or AHB bus. Okay, so either you take out the processor and do subsystem level simulation, or through force statements. Even if you have processor there, you are not executing anything on the processor, and you are able to force your stimulus on the AXI or AHB bus, and therefore you are able to control the various USB devices. Okay, so SOC simulation is complex. Normally, people with 5-10 years experience will not be mature enough or skilled enough to handle an SOC. So typically, you need a 10-year experienced person. Though if you are very smart, you may, or you get the right exposure, you may be able to handle it after 5 years of experience. But this is very complex stuff. Okay. Now in SOC FPGA, you you have the rest of the stuff ready-made, and it's actually not just ready-made. It's synthesized. It's implemented on your chip, and it's available to you. Okay, and only the programmable FPGA core that needs to be programmed. That's where you will be putting your design in, and that's what you need to verify. Okay, so you don't have the processor core as Verilog model. You don't have all this, the rest of the stuff as Verilog models. Most of this stuff is already built in into your SoC FPGA. So the point of doing what we are doing is, because this is a live processor available to us, just as in a normal SoC simulation, we were writing bare metal programs, and we were writing bare metal programs because in a simulation you can't hope to have Linux running. Linux in actual, like when we boot up a system, it takes about 10 seconds to run. In a simulation, it will take months to run. It will take months to boot up on a processor. So that kind of thing is not feasible. So you do bare metal, and because bare metal doesn't need processor to boot up, so you do bare metal, and bare metal will run on the processor model, and then it will exercise the bus, and your you'll be able to provide some stimulus to the application logic or elsewhere. Okay, elsewhere because you have done integration, and your application logic because you have integrated as well as its logic you want to test. Okay, now with SoC FPGA, the point is you don't need a model for anything. You have the actual processor, and you have the FPGA connected to it. So you can right away run your stimulus on top of the processor. And since it's already booted, since it's a full-fledged processor, so our idea is that why even some assembly language code? Why don't we simply create constraint random stimulus using UVM and run on this processor? Okay, so as it runs inside the chip, you don't see it, and therefore it sometimes becomes slightly harder to conceptualize or visualize it. Inside the chip, there will be AXI bus, there will be AHB bus. In our case, instead of APB, there will be Avalon bus, which will be connecting to the FPGA. And whatever we are passing from the processor, whatever data reads and writes we are making, those through the peripheral bridge will be signals in hardware inside the chip. So those tiny interconnects, which even if you take the cover off the chip, those won't be visible to the naked eye, but those interconnects are connecting your processor to the FPGA. So the idea of this small emulation board is where you run a UVM simulation on the processor, and whatever read writes or whatever stimulus had to be given to SHA3 in our example, since the Avalon bus is already in hardware, use that bus to exercise that stimulus on SHA3. Okay, now questions could be, are we checking the Avalon interface? Are we checking whether it works perfectly or not? Yes, we are. And actually we are testing the actual interface. It may not be getting stimulated, but this is the actual interface, and this is it is through this only that the stimulus will go inside the FPGA code. Okay, now when you do actual emulation in the industry, now, not that this is not actual emulation, but this can happen only on small modules like our SHA3 is. If you are doing SoC level emulation, then you don't, because the emulation platform, if it's FPGA, even if it's FPGA based, will only have FPGA cores available. Okay, so you map your design over there. You don't have a processor sitting right next to it. So then you have to bring up stimulus from somewhere. So there are two ways. One is the way emulation platforms are, there are ways to provide some sort of stimulus using, very costly tester kits. Like there are kits which are made by some vendors. Those kits will just generate Ethernet packets at a very fast rate. So it's not software, it's hardware which is creating Ethernet packets there. So it will be very fast. So one is that way, but that's not UVM based emulation or UVM powered emulation. The problem with that kind of emulation is, in case you have something failing, then it fails on the emulation board, and you have to debug it on the emulation board itself or emulation platform itself, because you are not doing a portable test. That test bench is in hardware, and that hardware cannot be taken to your simulation test bench. So in most of the cases, people who are doing emulation want to create a test bench in UVM based test bench only, so that they can provide the same stimulus to the DUT in an emulation as they can do it in the on their verification test bench, which uses the simulator as well. Okay, so you want to do UVM test benching in emulation as well as you want to do it for your verification test bench, which uses a Verilog simulator. Now, when you want to do that, since you are emulating the whole SoC, the processor is not available, you instead use an external server, you generate patterns there, and then those patterns, after converting them into Ethernet packets, for example, this SHA3 frame would in that case ride over a Ethernet packet or a PCI, depends on how you are integrating your emulation board or emulation platform with the server. Sometimes it's done through gigabit Ethernet, sometimes, 100 gigabit Ethernet, or sometimes it will be through very high speed PCI Express bus. Okay, it depends on how the emulation platform is integrated. So you will be sending those packets on Ethernet bus or on PCI bus, and then they'll be reaching the FPGA board. There, those packets will be ripped apart, and the actual data will be taken from them, and there'll be some logic to place them on the inputs of the FPGA. So that becomes very complex. Okay, so for small modules, our idea is that you can do it on SoC FPGA, actually at a higher speed than like the stimulus test bench, since you are using embedded UVM, which is an order of magnitude faster in test bench execution compared to system Verilog UVM, because of multi-core as well as because of other optimizations that we have made. For example, the lazy computation in UVM info. So because it can be done much faster, therefore, and it is easy to set up. So this is what we are taking up in this workshop. And this becomes, because it's so easy to set up, so this becomes a good learning tool as well as a research tool, because you can easily buy this board in a research lab for $130, and that's all you need. You don't need anything else. You need a laptop on which you'll compile, and then through Ethernet you will transfer your test bench, the executable of the test bench, to your board, and you'll just run it there. Okay. Um, a, a, a commercial verification emulation platform, for example, there is one from a big EDA vendor. It, in addition to buying the emulation platform, which will cost you at least $1 million, you will also need to set up a separate power station for it, because it will consume 10 kilowatt of power. Okay, at least one emulation platform needs cooling at 16 degrees. So the room you keep it in will need to be cooled at 16 degree, and it will be producing heat which will be in kilowatts. So putting an AC over there, because you have to maintain 60-degree ambient temperature, will consume again many kilowatts of power. So many kilowatts, uh, the emulation platform is generating, or it's giving as output, and many kilowatts will be required to cool it. Another emulation platform will be cooled by water. So you need a water tap in the same room, which will pass water to the emulation platform, and the cooling will take place like that. Okay, so those are, obviously those can take a billion gate design, and you can do a lot more. But with FPGA technology becoming more powerful, you are able to do decent emulation on FPGAs itself, decent amount of emulation on FPGAs itself at a much lower cost, especially with SoC FPGA. So that is what is part of is the agenda for today's lab, which will partly cover today, and partly will basically conclude it tomorrow morning. Today we'll synthesize our design, we'll create bit file, and before we do that, so I'll look at if there are any questions which are there, because this part is important to understand, like what are we trying to do. So we have the SoC FPGA only has the FPGA portion of it, which can be programmed. The rest of the design is already there. We are running our test bench on this processor. The executed test bench is creating transactions, which normally would have, in a Verilog simulation, they would have been interfaced with the running Verilog simulation, where that data which is generated in the test bench will be interfaced with the Verilog simulation, and through PLI it will get transferred to the simulation. Here in emulation, the processor generates transactions. The data which is getting generated is directly put on the AXI bus, and via AXI bus to APB or Avalon bus, and that data gets interfaced to the actual FPGA. There is an, just imagine an Avalon bus there. So data bus will get the data which will go into the FPGA along with the address decoding. All that logic will be there, and then it will get back some response. It will read back to the test bench. Okay, so having said that, I'll open up for questions if there are any, and then we will start with the exercise uh, of synthesizing our design in quarters, and we'll actually follow a tutorial, a step-by-step tutorial of managing everything. So let's take a look at any questions first, and then I'll go through that exercise. Okay, so this comment portion I already, so the questions about screen not getting shared, which I have done. Then there's a question about UVM info only. What is difference between debug and medium verbosity, and which one prints more messages? So when you are writing a message, if you say debug, that means it will get printed less frequently because you want to print it only during debug. So when you are giving a message or you're coding a message, then debug means you don't want it to get printed enough number of times. You want to get it printed only when you're debugging. Then there is verbosity level that you have to give while executing. And there, if you say debug, like I have said debug now. So that means everything will get printed because debug messages also need to be printed. So all other messages are also going to get printed. So debug is the most verbose in that sense that when I say debug, that means my verbosity level is highest. Okay, so that will print everything. When I say none, my verbosity level is lowest. Then only the messages which have been tagged with UVM none, only those will get printed. So now, now I'll I'll share my screen and I'll take you over to my browser, and on the browser we'll go to uvm.io. I hope everybody has downloaded the latest release. Uh, the latest release is there because there was a small gotcha because of which UVM factory was not working. So I fixed that bug and now your UVM factory is working. So if you want to run the UVM, any example where you want to use the UVM factory, you have to use the latest release. And also if you want to do anything with the board, since ARM binaries I've only released with this release, so take the latest release. And then we need to go to community. And inside community, I'll go to a particular tutorial that I put there a few months back and we'll follow that tutorial. So this is the tutorial. Turn your SoC FPGA into an emulation platform, DE10 nano version. All right. So we'll follow this tutorial step by step. And so first let me give you an overview. Some of you might have seen this tutorial earlier, but most of you may not be even aware of this because this is the first time we are talking about it. So this is a very detailed tutorial. We'll be setting up our environment for the synthesis, as well as we'll be using EDS because we want to create uh, the device tree, as well as we want to create that. I'm forgetting the name of the file that needs to be created. So there is a file which is required at boot up time. We need to create that as well. Then there is something about hardware settings on the board. So I'll switch on the camera and I'll show you where these pins are. So if you look at uh, this place, so there are switches out here, down here, where my finger is. You see these tiny switches out there. Okay, so these are the switches, and I've already configured them. They should all be positioned as on. Okay, so I already configured that. So this switch setting needs to be done because we want to. There are various ways in which this FPGA can be programmed, and this particular way that we are going to use requires this setting. All right. So then we are going to take the GHRD. We are then our the whole setup for the GHRD. Then we are going to modify it. and modify it with our SHA3 design. Okay, so we don't want to reinvent the wheel by creating our own setup from scratch. So that's what GHRDs with FPGAs are meant for, because you need to you need to have a way to start your whatever project you are doing, and you can start with GHRD and modify it to create whatever you want to do. And that's the principle we follow in this workshop also. We give you working projects so that you can experiment with them, create some differentiation by creating new test cases. For example, tomorrow I'll share SPI test bench with you. Actually, it's already on the GitHub, but only the stimulus part is done. So the rest of it you can start playing with. You can start adding a monitor to it and learn that way. And then after doing the GHRD modifications, we will do we'll create our IP. We'll integrate it into the Avalon system level, and then we add information into a tickle file. This will be important to automatically generate the device tree and stuff like that. Then we make custom connections into, just like what Ritesh was explaining yesterday. The same things we'll be doing practically for our design now. Okay, so taking we will be making these connections so that our Avalon SHA3 module gets connected to the system via Avalon bus. And then we generate the HDL. This will be the top level HDL at the system level, which integrates the design, and then we synthesize everything. After synthesis is over, yeah, this was the file I was talking about. We need a preloader or BSP, which will be automatically generated there. So then, after doing all that, we will take an SD card, and we will put all the stuff on the SD card. Okay, and I think some figure is not visible here. I'll have to check what that figure should be. And then we we want to create our test bench, and for the test bench we will be using GCC for ARM. That needs to be there along with the test bench compiler LDC2, and the LDC2 version of we need to have libraries with LDC2, which we downloaded today, the ARM libraries, and then we will compile the test bench. But before that, using the Linaro release, we'll be compiling the U-boot, and finally we'll be doing device tree, and we'll dump the whole thing on an SD card and run it on the FPGA. Okay, so it's a big exercise, and this looks like some image is missing here, which I'll check what image it could be. Okay, but anyway, it looks like self-explanatory. So a couple of images not getting visible here. Okay, so now let's go from the top. You can map your RTL IP into programmable logic part of your Cyclone 5 processor. This is what PL or programmable logic is meant for. Here you will learn how to map an embedded UVM test bench on the hard processor system or the HPS of Cyclone 5, thus converting your DE10 nano board into a small but efficient emulation platform. For the purpose of illustration, we have taken SHA3 IP from the Cryptech project, and Avalon Light interface has been added around the IP. I already, on the first day itself, I had shared the ID, IP, and I've shown the wrapper file which implements the Avalon interface, so that it can be integrated into Cyclone 5 FPGA and accessed from the HPS. HPS is the processor, remember? You can clone the RTL from this place. That is, it will have the Avalon wrapper as well. Note that the Git repository also contains embedded UVM test bed that runs with Icarus Verilog for the purpose of testing the RTL design. But when we do this, we'll take the test bench from there, but our test bench now we have evolved it. So now we have factory and everything. So all that will also be done. For the purpose of emulation, we'll be modifying this same test bench and running it on DE10 nano board. But before that, we need to go through the process of synthesizing and mapping the RTL into PL. So the tools we need Quartus Prime. We will be using the light version, which is free. We need the SOC FPGA Embedded Development Suite, the EDS, and we'll be using 18.3 version of both the software suites. You may, so basically we are on Linux, and the latest version that we could use is 19.1, but I'll be using an older version, which works good enough. Okay, so first part is installation of the Quartus Prime. Okay, so then you want to install ADS. So I'll assume that both are there. So let's see. So I have a system called module load, and then I have Intel, and from Intel I want to get Intel FPGA, okay, and I want to get FPGA Lite, okay, 18.1 version. I have 18.1 version, so I will be using that. Okay, and Intel FPGA, what was the version? 18.1 again. Okay, so these are the two tools. All right. And with these two tools, so my module command will make sure that these two tools become available to me. So now I'm able to say Quartus, and Quartus will run here. All right. I hope the font is big enough. So I had customized the font from this interface, and font here is 10. So I'll make it bigger. So I'll make it 16, and font here was already 16. Okay, so I'll say okay, and I'll come back and exit because I've changed the fonts. I need to run it again. So my Quartus is already there, and the comments are going to come here actually. So is there a way to move this up? Yeah, this way, this way. And is there a way to this one? Okay, so I wanted a way to maximize this window, but I don't think that is necessary. So let's start with the exercise. So we need to get the Terasic GHRD, that is the system CD, and that's available here. Okay, so since you people don't have login because you don't have the kit, you won't be able to download it. But I'll download it because I bought the kit. So it's available here. So there are many boards over here. We are interested in SoC platform for Cyclone 5, and this kit is the one which we'll be using is the Nano kit, this one. Okay, and we go to the resources. So first let me go to the kit, D10, D0, not 0, D10 Nano kit. Okay, Now I'll go to the resources, and from the resources, I want to get the CD content, the GHRD content. So that will be their release notes, authentication signature, license, SD card image, and all source code required to rebuild the Linux image. So I don't need this, any of these two for now. I need the CD, which one is that? These are documents. Then we have certification. Yeah, E10 Nano CD-ROM. Okay, this is angstrom image, which I don't need right now. Certification resources, champion designs. I don't need any of these, and I need the CD-ROM. Okay, so DE10 CD-ROM. I need it for a particular hardware, and this I need to identify what kind of hardware my kit would be. So they tell you that you have to know the serial number of the kit, and from there you can identify what kit you are using, what kind of hardware you are using. So there are three versions: revision C. I know I have this revision B2. Okay, I know it is B2, so I'll be downloading this. But otherwise, there is revision C and revision AB. So I know I need to download revision B2. So I'm downloading that. Okay, so it asks me for password. So I have a login, but I won't be downloading here because here it will come on my Windows PC. I want it to go to my server. So what I'll do is I'll go to my VNC, and inside VNC I'll close quarters for the time being, and I'll try to run Firefox here because I want the download to happen here. Okay, and from here I go to Terra 6 and from here I go to Cyclone 5, and we are using the DE10 Nano, DE10 Nano. Okay, and this one we have resources, and from the resources we want the CD-ROM for B2. Okay, so I click here. Okay, so I'll put my email which I use here at overify.com, and there is some password. So I put a password. No, it can take it, it can type it. So I put another password. I hope I don't have to reset my password. I hope I remember it. No, not this one as well. Yeah, okay, check this one. Yeah, it went through. So now it's saying it wants me to download a file. So I'll say okay, and it downloads it. It will be quick. So it's almost half done. All right. So we already have the CD image. So we close the browser and we come here, and inside our Filna Slash downloads, you will see the CD image in the end, DE0 Nano, this one, this file. Okay. Now we'll go to the workshop directory and we'll unzip this file there. So let's just move this file there. Tilde move tilde slash downloads and this file, this file, to move to tilde to go to the present directory, and then I unzip it. All right. So as a result, hmm, actually, this is not good because this corrupted my space. So I'll remove whatever was created. So remove minus rf data sheet demonstrations manual schematic tools and verify. So I'm having what I had earlier. So I'll create a directory, and that directory is d10 memo. And inside this directory, only I'll unzip the file. Okay, so that my stuff is well contained. So you can see the stuff here now. It's well contained. All right. So now, since we'll be incrementally modifying it, so what I want to do is I want to check everything into Git so that I'm able to track my changes. Okay. So let me do that. Git init and then git add dot. So it will add everything. It's going to take a bit of time because this is huge amount of data. Okay. Then I say git commit minus n as downloaded from TerraSync. DEN nano V2 version. All right. So all these files were created and everything is in control now. So we have a .git directory now, which has all the content as we downloaded. All right. So let's take one by one all the steps. Let's replicate the steps and let's see how it goes. So we need to go back to uvm.io and we go to the community website and there we go to this example. Okay, so we have done all this. We have installed Prime ETS as well, and then we have obtained the GHRD, and so it says to find out A, B2C version. Uh, it's written on the back side. Okay, so where is it written? I can't figure it out so easily. But anyway, I know my board is B2 version. So let's go ahead. It says version flip the board. It contains a seal mark on the back side. Seal mark on the back side. Where is the seal mark? I can't figure it out. Anyway, so we go with V2 because that's the version I have. Then IP integration in Quartus, load the provided design in Quartus Prime, open project file named this. Okay, so we'll do that. So here we go. We uh, we need this file. Where is that mentioned? DE10 associate.ghrd.qpf. So to find out where it is, I just say find DE10 nano star dot qpf. Actually, this is not a command, this is not the way to do command minus find dot minus name. So here it is inside the demonstrations. Okay, so that's where we will be picking it up from. So it says load the design. It's recommended to upgrade IP as this design was drafted in version 16, whereas we are using 17.1, and actually I'm using 18.1. So we will load the design first. So we'll run quarters. We'll go to demonstrations, and there we'll run quarters. And here I need to load the design. Open, and I need the QPF. Okay, and why it's not showing me where I'm inside demonstrations, and it should show me here, right? QPF, DE10, and all that. Let me. This is crazy. So it's showing me FPGA, SoC Advanced, and SoC FPGA. But it's not showing me that particular file. What's the matter? Demonstrations. So it's not in demonstration, it's somewhere else. Where did I find it? So it's inside FPGA ADC or SoC FPGA, then control panel. So we need to take this one, not this one as well. This GHRD. Okay, so it's inside demonstration SoC FPGA, SoC FPGA, DT10 nano SoC GHRD, and there. Okay, so I'll open that. Quarters. I need to go inside demonstrations. I need to say file open, and I need to specify QPF here. Need to go inside this. Then I need to go inside SoC FPGA, and then DE10 SoC GHRD, and then I need to open this file. So it's opening. Okay. Now, as our instruction said, it will ask you to upgrade, recommended upgrade IP. Okay. So we'll say launch IP upgrade tool. Okay, it will give you a warning, but don't worry, perform automatic upgrade. So it will take a bit. It's upgrading. 37% complete. Still 37%. Still, it is showing 37%. I don't know why. It's working though because the screen is scrolling. So don't need to worry. So it doesn't look like we'll be able to finish this exercise today because only 15 minutes remain. But we'll be able to start it, and tomorrow morning we'll be able to finish it. 2 EMU won't take too much time, and I'll be able to squeeze in some stuff on casting, on basically on polymorphism and upcasting and downcasting. So I'll cover that tomorrow. So now 65%. Okay, done. So we need to close it now. So it has upgraded the IP to the latest version. And now we look at the next step. So this portion we have completed. So modification of GHRD in QSys. To modify, we launch QSys. So tools, and in tools we want to go to QSys. I think there's a platform designer, they renamed it. Okay. So once we do that, open file inside Quartus. In case if you don't find QSys under tools drop down, go to files, open file inside. Go to file, open associatsystem.qsys. File, it's already there. Associatsystem.qsys, open. Okay, so sorry again, it's small font. So I'll try to change the font size. Options. I can't because there's no option over here for fonts. So let me check at other places if there is an option to change the font size. So inside edit, view, custom layout. So it doesn't look like that there's a way to change the font size. At least it's not obvious like how to change the font size. So I hope we'll be able to uh, use this only. So we have uploaded what the step we have completed is we have uploaded, uh, we have opened the file, we have opened SOC and the reference design is it has a component in place of LED PIO. On the bottom left under hierarchy tab, you will find LED PIO. Right click and remove. Okay. So what we are doing is we already have a component which is called LED PIO. we are going to remove that from our design. Okay, so we need to look for LED PIO somewhere here. LED PIO. Yeah, this one, LED PIO, and right click and remove. Okay, so that's what we did. So we'll be, instead of LED PIO, we'll be having now SHA3. So let's see how to do it. Creating a custom IP, download this file with this tutorial. So we have to download Avalon sha3.tgz, and this basically we can also download from GitHub. So this is where to download it from. Okay, Avalon sha3, this place. So the same that we had, and in source we have RTL, and inside RTL we have the three components: Avalon SHA3 wrapper, SHA3.v, and SHA3 wrapper. Okay, so these are the files we need to synthesize. So going back, so it wants us to use those files and extract it, custom component creation, uh, files, add the files, add button under file, synthesis file, select all the expected files from here. Okay, so this is what we'll be doing now. Okay, so this actually is using slightly different files than what we have right now, but we'll use whatever we have right now. So because that's what we ran the test bench on, and I need to go to the terminal, and I need to pull in my, so I'll create a directory here inside demonstrations, or let me create a new. So I'll create a directory, name it SHA3 RTL, and we'll go inside that, and I'll copy all my RTL files. Copy from tilde code, and there you have not code, workshop, workshop, AVMM SHA3 source RTL, and these three files from here. So SHA3, these three files, these two files, wrapper, there's Avalon SHA3 also, the third file RTL, and then I need to copy all the .v files. Okay, so I got three files and I want to use them. So basically I'll add files, go to files, add files. So first I need to go here, uh, click file, choose new component from drop down menu. Okay, so I go here and I need to have quarters, uses, file, new component. All right, and therein I need to component editor as add component information, go to file, click add file. So component information, name of the component is SHA3, and display name, let's put it as AVMM SHA3, and then version, this group not required, and description Avalon SHA3, and created by, I'll put my name, icon, there is no icon, There's no icon available for me. And then go to files and add file. So I need to be here and inside SHA3 RTU, I'll pick up all these three files and say open. All right. So then the instruction says um, add file, synthesis file, and then select all the files, and then top level file under attribute tab, select the files for our project. Top level file is evalon.sha3.me. So we go back here. The top level file for us is evalon.sha3 wrapper, and so top level module. So what does it say? Let's go over it again. Look at the top level file, add the components in the component file, go to files, add files. Click on add file button under synthesis files, select all the files. Look, look for top level file under attributes tab. So there must be some attributes tab. Where is that? Source attributes, top level. Yeah, this is the top level. Top level file contains inline configuration package, nothing. Okay, and then select that file for our project. Top level file is this. Click on analyze synthesis files. So we click here. Error interface must be having an associated reset. Okay, so we have some problem where we don't have an associated reset, and we'll have to go and modify our stuff because our RTL doesn't seem to have a reset. Okay, so let's do that. Edit dot. So there is a reset. It may be that it needs to be named differently, but let's see. Actually, this was earlier done for a different version of quarters, so maybe because of that. Uh, so what is the error that we are getting? We go to platform designer, then the error is error interface must have an associated reset. So we need to go to signals and reset. Yeah, yeah. So we need to associate this reset with S0. Okay. So how do we do that? Allow editing and reset, and associated clock is there. So this one, associated clock, associated reset is not there. So we're just going to select reset from here. All right. So having done that, we'll analyze the files again. Okay, now it finished without errors. So we close the thing. And now we go back, follow the instructions. So analyze is complete. Under the signals, we set read latency to 1. Okay, so we go here under the signals. We need to set read latency to 1. Read waveforms, write waveforms, and read latency maximum. So this value we need to set to 1. All right. 1. And then we need to finish it, and we should see the component in the component catalog after that. So we need to finish this activity. So message, yeah, component type, block, looks okay. Files, everything okay. Parameters, no parameters required. This one is also okay. Now, how do I finish this? Here, finish. All right. So it says you are about to save Avalon SHA3 1.0. The following files will be written. SHA3 hardware.tcl. You want to save? Yes, I saved. Okay, so my activity, this activity is finished, and I see a new component here. So what has happened is I have uploaded my design files into Quartus, and now the synthesis has to be done. Okay, since it's already 2:30, we'll close now, and by tomorrow we'll complete this activity. It should take, the morning half of tomorrow's session, and then in the evening half, in the afternoon half, we'll cover QEMU, which should, because that doesn't require any synthesis, etc. So it should be done more quickly. So it will take about 1 hour, and then we will cover uh, uh, casting, upcasting, and inheritance in slightly more details. I already have slides for that. I just need to go through those slides with you people. So that's it for now. I'll be back tomorrow with, and we'll cover this, and we will finish this whole thing tomorrow. Okay. So Firodaji, I'm done for now. Okay, there are a couple of questions.
Yeah.
Yeah, there are a couple of
Yes.
questions. I'll take those, and then we can end the session. So
Oh,
since we
yeah.
don't have
Okay, sir.
FPGA
Okay.
board, can we run this new test bench on our system? The new test bench you'll be able to run on your system, but since the part of the interface with FPGA is not enabled by default, that's why you will be able to run it. But once you enable it, you need a kit. Okay. And the next question is, can we map an embedded UVM test bench in DE2 Cyclone 2 FPGA board? I don't think, because Cyclone 2 doesn't have a processor. Cyclone 5 has a processor. Okay, so either you need Cyclone 5 DE10 nano board, or DE10 standard board, or DE1 SoC board, which is again based on Cyclone 5. Cyclone 2, certainly not, because it won't have FPGA. I would request you to send the step-by-step procedure in a video document format. It can help us. I'll do that. I'll actually, after completing this exercise, what I'll do today itself is I'll make the tutorial specific to the RTL we are using, and that tutorial will have all the details. Okay, so that's it for now.
Yes, sir. Thank you, sir. So, sir, there is any more question like?
No, I have covered all the questions.
Yeah. Okay. Thanks a lot, sir. And dear participant, there is an announcement again. We will be having another MCQ tomorrow, so please be ready for the same. The MCQ time will be same from 2:45 to 3:15. So I request you all to please join, and the MCQ result for yesterday has not been yet uploaded. We will upload you the same by today. We informed that due to heavy rainfall, we are facing some issue with the bandwidth. Just after this class, we will do the same. So sorry for the inconvenience caused, but the class was more important. So after this, we will be uploading. So thanks a lot to all. Thank you, Puneet sir. And we will be joining tomorrow sharp at 10 a.m. I request you all to please be connected by 10 a.m. so that we can start the session by 10 a.m. And for all
Actually,
the recorded lectures, I request you all to please visit the YouTube channel. Sir, Puneet sir, please.
yeah, actually, there is a spillover also for today. We couldn't cover everything that needed to be covered today. So because of the
Okay.
spillover, please come on time so that we can cover everything.
Yeah, I request you all because daily almost 10 minutes Puneet sir wait before delay starting the new session. So please be connected by 9:50 so that we can start the session by 10.
Okay.
Okay, thank you,
Okay,
sir.
good
So
night,
with this,
everybody.
we conclude, sir. Thank you.